Well, ladies and gentlemen, here we are. It is Thursday night, and we do not have school tomorrow on Friday. But the stats must go on. So let's see if we can learn the lesson about confidence intervals for a proportion vis-a-vis YouTube videos. So we have in October 2015, the Pew Internet and American Life Project asked a random sample of 971 adults. Let's pause there. 971 is an important piece of information. That will be our sample size. And it is a random sample, thankfully. The question was, do you ever use Twitter or another service to share updates about yourself or to see updates about others? This was in 2015. I'm guessing these numbers are a little bit higher now. Of the sample, 65% said yes. According to Pew, the resulting 95% confidence interval is calculated for us as 0.614, 0.686. We're asked to interpret the confidence interval in context. Well, we would say, as we learned Thursday in class, we are, pardon my handwriting, we are, let's see, 95% confident that the interval 0.614, 0.686, that this interval will capture the unknown population proportion, or just unknown proportion of all U.S. adults, who would say yes to the question. And that looks like horrible handwriting, but I hope you get the idea. Next, so that's interpreting the interval. Really important, you can tell the difference. That's interpreting the interval. Now we have interpreting the level. Interpreting the level is a 95% level. So we would say, oh, I should type this. This will be much better. Interpreting the level would be, maybe I'll just type it right here. Interpreting the level would be, let's see, in repeated sampling, about 95% of intervals will capture the actual proportion of all U.S. adults who would say yes to the question about Twitter stuff. So that's interpreting the level. The level is about the percentage of intervals. Now, a lot of this, it could be 95% of samples will produce an interval. You could say something like that. Sometimes on a multiple choice question, it could throw a couple extra words in there. I might say, will produce, yeah, okay. So we'll just leave it at that. I don't want this video to be too long, right? Letter C in 2014. So the data that we have is 2015. In a random sample, 62% of adults who answered yes to the question, do we have evidence that 2015 saw an increase in social media usage among adults? The issue here that you need to observe is that the interval that we're looking at is this interval. Any value in this interval is a plausible value. In 2014, it was 62. So even though there are higher values, like the 68, even though there are higher values, it's just as likely that in 2015 it was 61%, which is not an increase. So do we have evidence that 2015 saw an increase? We would have to say no, because it could have been that endpoint, it could have been 61%, and that would be a decrease in 2015. Next question. This says the figure at the right shows the result of taking 25 SRSs from a normal population. You can see the normal population drawn for you right there, normal population. Constructing intervals, so here we have 25 intervals. What do you think the confidence level was? 50, 80, 90, 95, or 99? Why don't you pause this video and see what you think. Note that the population parameter is this line right here. You should have said probably the best guess, since it looks like all 25 out of 25 capture the parameter. Probably the best guess is that it's a 99% interval. It's possible that it could be a 95%, and we just didn't have any. We'd expect 95 out of 100 approximately. But I think 99 is our best guess. Our lesson for today is the formula for a one-sample z-interval for a proportion. This formula is not on the formula sheet. The components of the formula are. The formula should look familiar, actually, from our GPA sampling activity. The formula is our estimate, plus and minus our margin of error. I'll just put ME for margin of error. Our estimate for a proportion is p hat, plus or minus our margin of error. The margin of error is the critical value times the standard deviation of p hat, the standard deviation formula that we learned in the previous chapter with sampling distributions. So I've quickly run out of space here, so let me kind of continue writing up here. So the formula is this: p hat plus or minus z star. Z star is the critical value notation, times the standard deviation of p hat. That is a formula that typically would be p times 1 minus p over n. However, since we are estimating p, we don't know the actual proportion. We use p hat as an estimate, and then this would be called the standard error. But this formula right here is our formula for a one-sample z-interval for a proportion. It's your responsibility to memorize this formula and to know the name of the formula. You could be asked on a multiple-choice question what type of interval should be constructed, and the answer would be, in words, one-sample z-interval for a proportion. Now, this interval is only accurate if certain conditions are met. So let me get rid of this stuff for now. So the conditions to construct this interval: the p hat. We want p hat to be an unbiased estimator, so we need, and I'm kind of down here now, we need a random sample. This is called the random condition. We need a random sample, like a simple random sample, or we need random assignment if it's an experiment, random assignment of treatments. So to justify that this estimate is a unbiased estimate, we need to make sure we have some kind of randomization, or at least that our sample is representative of the population. Next, this z star is how many standard deviations we want to go. You might remember I had you use a 1 standard deviation that gave a 68% confidence interval, or a 2 for z, and that gave 95%. But here, z star, we would need to check what we call the normal condition, because it wouldn't make a lot of sense if we were talking 68% of the data is within 1 standard deviation. That's only true if it's a normal distribution, or roughly normal. So the condition we check should look familiar: n times p is greater than or equal to 10. If that is true, and n times 1 minus p is greater than or equal to 10. But again, we don't know p, the parameter. We know p hat, though, so we estimate this with p hat. So if both of those are true, then our critical value is accurate. And then the last component is this piece. This is the standard deviation component. This formula is based on the assumption that you have independent observations. Uh-oh, what did I do? Everything just erased. Shucks. So that formula, I guess I can scroll down now. Maybe. Oh, maybe not. So the independent condition, so this formula, p hat 1 minus p hat over n, we check the independent condition. We need the observations to be independent. However, if we're sampling without replacement, then we check and make sure that our population is large enough, which is the 10% condition. 10 times the sample size needs to be less than or equal to capital N, which is the population size. What happens if one of these conditions are violated? They're really ordered. So the very first thing is the random condition. If you don't have a random sample, really you shouldn't be doing anything with confidence intervals. There's no reason to think your interval is going to give you a good estimate. So that's probably the number one condition, the most important. The second one is the normal condition. If the normal condition isn't right, then your interval isn't very trustworthy. You don't really know if your z star is like a 1 or 2, 1 or 2. You probably will not have the correct capture rate if the normal condition. Capture rate will actually be less than you expect if the normal condition isn't met. And lastly, the third, and probably the least important condition, we'll still check it, is that independent condition. If the independent condition isn't met, and you think your interval is like here to here, if the independent condition or 10% condition isn't met, then probably you've sampled way more of the population than your interval is taking into account. So in reality, your interval is probably shorter if the independent condition isn't met. But really, that's not too big of a deal, because if you think this is the interval, but in reality it's even better than you thought, then you don't lose too much. You're just being a little too conservative. So those are the conditions. So those three conditions we'll be checking from here on out. So memorize those and make sure you get used to those. What's the difference between standard deviation of a statistic? Well, standard deviation of a statistic p hat would be this, which we saw in chapter 7. That's the standard deviation of p hat. The standard error of the statistic, we could write SE for standard error of p hat. That would be a very similar looking formula, but now we're just estimating p with p hat. Since we don't know the proportion we're estimating that, we use p hat. How do you interpret this value? Well, remember, it's a standard deviation. So we would expect our p hat estimate to be about this amount, whatever this amount is, to be about that amount away from the population proportion. In this formula is on the formula sheet. However, this one is not on the formula sheet. But again, I would recommend just knowing either one or both, actually. So let's check some conditions on the next question. Check whether the conditions for calculating interval are met. Why don't you pause this video, read number 1 and 2, and see what if all the conditions are met. Number 1 probably breaks the most important condition. If you're going to do a convenient sample, then why are you even sampling? The random condition is not met. I included over here the normal condition. We would have a sampling distribution that is roughly normal, but we have no reason to think that p hat is going to give us a good estimate at all of what we're trying to estimate, since we did a convenience sample. Go ahead and pause and try number 2. Number 2 has a random sample. It makes us happy. But however, only 3 successes. 3 had too much salt. So if we're going to try to use a sampling distribution of p hat, remember our condition NP hat needs to be greater than or equal to 10. That is not met, so we are rather sad. There are enough failures, but not enough successes. So in that case, we wouldn't know what our z star should be. Since we can't use a normal distribution, then one standard deviation isn't necessarily 68%. If it's skewed, it could be more or less than 68%. We really don't know. So on the next part, we're going to be talking about how do we actually calculate that z star. So what is the critical value? Well, the critical value is important because we use it to calculate margin of error, so that's incredibly important. You might remember the critical value when we did the sampling GPAs activity. When we had 68% confidence, that was a 1 standard deviation away. That was a critical value of 1. When we had 95% confidence, that was a critical value of 2. That's how many standard deviations away you want, and basically how much confidence you would like in your estimates. What's up with the star? The star is because the z here is not based on real world data or anything like that. It is a z score, but not based on some observation. It is based on theoretical confidences that we want. So z star. This is a notation issue. How is it calculated? A little tricky here, so be careful. Z star, it's a z score. So if you think of a normal curve, if you want, let's say, 68% confidence, we want to know where is our z star? Where is the z star? What is the boundary? If we had 68% confidence, now we have to be really careful here because the calculator will give from negative infinity up to that z star. So the issue is this: we have to factor in this left tail, what area that would be, because this inside part is your 68% confidence. But again, the calculator, it's just a calculator issue, the calculator needs to know, to give a right answer, it needs to know this area. So you have to do a little math here. 68's in the middle, that'd be 32 on the two edges, so there's 16 over here, 16 over here. So to find this critical value, we need to use inverse norm. Remember, we use inverse norm when we know the percentage, but we're looking for the boundary. Inverse norm, the area would be not 0.68, but 0.68 plus 0.16. I believe, if I can add correctly, that would be an area of 0.84. And then our mean is 0, it's the standard normal curve, and our standard deviation is 1. So why don't you do that on your calculator, and you should get something very, very close to 1. I think it's 0.994. Let me look at another example. Get rid of all this. Let's say we wanted the let's not do that. Let's say we wanted the 95%. We wanted the critical value for 95% confidence. So we would do a little sketch. Here's 95%. When we type it in our calculator, though, we have to tell the calculator this little area piece and the left tail, because the calculator will tell us this z score, this z star. So let's see, mental math. 100 minus 95 is 5. Divide by 2, so that's 2.5, 2.5%. So we need an area of 0.975. Barely fit it on the screen. And the mean is 0 and the standard deviation is 1. And when you do that, you should get very, very close to 2. Actually, you get, I believe, 1.96. 1.96 for the z critical value. That is actually the more common value. Instead of 2 standard deviations away, 1.96 is a very common value used in confidence intervals because it's slightly more accurate. So, why don't you try to calculate the z-star for these two weird ones? 96% should be a little bigger than the one we just calculated, right? Because you have a little more confidence. 84 should be a little smaller than that. So pause this video and see if you can figure those out. Here are the answers. You should have a z-star for 96% confidence and z-star for 84% confidence. Remember to factor in the left tail on both of those when you're using inverse norm. We're almost ready to do a full word problem, just like FRQ number 2 on the 2017 exam. Required students to do something like this. Before we do that, just a quick review about margin of error. The margin of error gets smaller margin of error when the confidence level decreases. So if you have less confidence, means a smaller margin of error. If you want to be really confident, then you're going to need a really big interval to be really confident. The margin of error gets smaller when the sample size does what? Well, remember, the margin of error is based on the standard deviation of the statistic. So if you increase this goes up, this whole quantity will decrease, which would decrease the margin of error. So as the sample size increases, you get better estimates. Your margin of error decreases. You have more accuracy, less variability. Alright, I think we're ready now to look at a full FRQ. I would like to focus on question A, because that's the new stuff, but we'll answer Z as well. Why Z? Because I didn't want to have to retype all the letters, and I already had A, and I needed something before A, so obviously that's Z. Anyway, what percent of the 943 Classical Academy underclassmen have a 4.0 or better? And this is weighted GPAs. You can have a 4.0 or better. A simple random sample, of 50 GPAs revealed 20% of the students in the sample had a GPA of 4.0 or higher. Important things to note. This is our total population. That would be capital N. We have a random sample of 50. That would be our lowercase n is 50 GPAs. We have 20% from our sample. That would be our p hat. And all the other numbers, like these 4.0s, those don't really matter. Identify the population. The population is all of these Classical Academy underclassmen, all 943. The parameter of interest is the actual proportion, the actual p, not p hat, but the actual p proportion of CAHS students with 4.0 or better, 4.0 plus. That's the parameter of interest. Really important. It's nice to use the language of actual or true or unknown proportion. Unknown proportion, etc., etc. So let's focus on A. That's the brand new part of today's lesson. Calculate and interpret a 99.7% confidence interval for P, the true proportion of students with GPA 4.0 or better. Assume conditions are met. Oh, I'm being really nice here. Just to quickly go over the conditions, it was a random sample, number one. The proportion of successes, we had 20%, and it was a sample of 50 times 20%. That's 10. That's exactly perfect. And that would mean if 10 out of 50 had a 4.0 or higher, that would be 40 out of 50. So 40 is greater than or equal to 10. So all the conditions are met. And we have a lot of students at the school. There's 943, and that is Our sample is not 10% of the population. But anyway, those are the conditions. Calculate and interpret a 99.7 confidence interval. So we need to do this. We need to do p hat plus or minus z star times the square root of p hat times 1 minus p hat all over n. And that z star, let's find that first. Z star, we do a little normal curve. We want 99.7, 997. So that leaves 003 for the two edges. I believe that would mean this one has 0.0015. So I'm going to do inverse norm of 0.9985 if I added that correctly. And I get a z star of 2.9677. My p hat from above was that 20%, so I can come back here. We have 20% plus or minus the z star, put that in parentheses, 9677 times the square root of, I had 50 in my sample, 20% had the GPAs high enough, 80% did not have GPAs high enough. Multiplying that out, I would get that number right there, just so you can check your work. I got 0.5656, etc., etc., etc. Multiplying to find the margin of error. The margin of error would be this amount, a rather large margin of error. So that right there is the margin of error. And then to find my boundaries, I would do 0.2 minus that answer. So that's my lower bound, 0.03, comma, and my upper bound should be 368, like that. So this very large interval. I mean, notice that's quite the interval. It's pretty big interval. That's probably because we wanted so much confidence that our interval is huge. So to interpret this, definitely my recommendation to use the wording of the question. We would say we are 95, oh, not 95, we are 99.7% confident, right there, that this interval, right there, captures the true proportion of students with GPA 4.0 or better. Don't feel bad for copying it directly there. Students who copy it directly there tend to score higher than students who forget to use any context at all, for sure. So again, we are this percent confident that this interval captures the true proportion of students with GPA 4.0 or better. How about you finish the questions on this page, and I will finish this video. Thank you for your attention, and I hope you have a fine day off.